Hi, my name is Sean, and I'm a gameplay programmer with Digital Confectioners. And I'm here to talk about melee hit detection and our system that I've worked on for our upcoming project that is an action-based RPG. So today, first we're going to go over our goals and our challenges. Then we'll look at some common solutions that are already implemented in the engine that we can use. Then we'll look at our solution and how we built on top of those common solutions. And then we'll look at some code and then do a reflection. Hopefully by the end of this talk, you've gained an understanding of melee hit detection in games, and understanding of how to build performant and lag redundant systems, and some good practices when handling data for high performance. All right. So our three main goals were accuracy, performance, and lag redundancy. So for accuracy, it's really important for a game like ours where we're very action-based, and so the players are going to be expecting highly accurate hit detection. We want to be performant because it's important to maintain a high frame rate for us because of high stakes action combat, and to keep our frame dips as minimal as possible for a smooth gameplay experience. And we're also going to look at lag redundancy, because sometimes unexpected lag can happen where the game might hitch or we lose a few frames, and because when that happens we lose data, we want to minimize that as much as possible. Okay. And for our challenges, it's always a trade-off between accuracy and performance. The more accurate we try and make our system, typically the more performance it's going to cost, and the more performance solutions will end up lacking in some accuracy. And our other challenge is actually config. And I think config is often something that is overlooked, because as an engineer, we spend our time thinking about how much time investment is actually going to be required to make our system. But there's also the other side where we have our combat designers, and how much time are we going to need from them to be able to configure our system for actual gameplay. All right, so have a look at some common solutions that are already built into the engine. First up, we have hit events. And ironically, hit events are not actually that appropriate for the type of hit detection we want to be doing, because it requires physics simulation on both the weapon and the character or object that is receiving the hit collision. And we also require for the collision to be blocking as well. You can work around this a little bit with some hacky solutions to still have a physically simulated actor in your character's hands, but it's really hacky and it's not recommended at all.
Overlaps. It's probably the most typical solution. You define a shape, either on maybe you're using your mesh or a shape component as your collider, and then you either just generate overlap events or you can manually call them through code. We ended up calling them through code, which we'll see why in a minute. But generating events is perfectly fine in some cases. They're pretty fast still. The only time you really run into issues with overlap events and performance is if you have a poorly configured collision profile. So making sure you're not overlapping every world static object or checking overlaps against it, for example. And everything's already handled by the engine as well. That's nice. But the big issue with overlaps is if you do an overlap in one frame and then you got to do another overlap in the next frame, they have no regard for anything that happens in between them. And you can enable CCD, which is continuous collision detection. But that is a really high cost, and you kind of have to rely on only using generated overlap events. You can't call it manually through code or anything like that, which we will end up wanting. And there's no accurate hit result info from overlaps either. So if you want an accurate location from your overlap, you kind of have to either like figure it out, like maybe find nearest bone. But if the origin of your weapon is, say, in your hand and the blade so far away is hitting the character, you might end up finding the wrong kind of location on that hit enemy. All right. Yeah, let's have a look at sweeps. So very similar to overlaps, but when you call them through code, you get like, just like CCD, you get the collisions in between. But some other nice things about sweeps is you actually get a hit result from them. So if I was to hit an enemy, it's not a perfectly accurate hit result, but it's close enough that you can kind of fudge it and figure out like a close enough location for your VFX or sound or whatever. All right. So sweeps are great, and I use sweeps a lot, but they actually don't meet all of our goals. And the main one is the lag redundancy goal. But we can build on top of sweeps and get a much better system with that by doing our own work to add some lenience for players, handle the lag better, and we can also do some like arm detection, which I'll get into that a little bit more, but it also ends up being a really, really important part for our head detection. All right. So lenience and handling collision data are kind of lumped in handling collision data here. We can actually cache a lot of our data for collision up front with a weapon, like on begin play or whenever it changes owner. So we don't have to constantly go out and reference our mesh or the component, the shape component. We can actually just have all that data locally stored on the weapon, and it's a quick lookup. And then that also lets us actually mess around with that data quite easily as well. So we can have a nice and tight collision for our weapons, the weapons on our enemies, but we can inflate it a bit for our players and make it feel a little bit better. It's not like the perfect hitbox in the player's mind, but it feels significantly better. And of course, we also have the tight collision for our like physics interactions. So lag redundancy, this is the biggest part, I think. So whenever we hitch and we lag using sweeps, we still have one big issue, and that is we can still miss some of our hits. So let's envision like I have my weapon in my hand. I start frame, and then I hitch for the entire attack until it ends up in the other hand, other direction. What will actually happen is the sweep will go directly from the first location to the end location, and you won't get any of the swing information in front of you. So ideally, we fix that. So here's actually a GIF of what we have. There's a lot of sweeps happening there, but we can change that. So when doing an attack, we can cache to position of the weapon socket for each frame at a regular frame interval. And this information is based on the animation, actually. So we can call into the animation, cache that pose data. And then when we go to actually do the sweeps, we can say, okay, we've reached at this point in time, perform a sweep. And we can keep doing that at the regular intervals that we cached. And if we ever lag or skip over them, we can go back and play catch up. And arm detection. So kind of in one of the issues that we ran into was what happens with the space between the weapon and the character themselves when they're doing a swing. Well, a first solution that we came up with was just to extend the hilt of the weapon, or the collision of the weapon. But that ends up having some issues, like what if the weapon's actually rotated away from the character, so you end up like hitting things you don't want to and still missing the things that you do want to hit. So we can use the same predictive behavior that we had on the weapon socket and use it for our wrist and our shoulder or any other kind of arm on a character. And we can use those cache positions and figure out like a rough hitbox for our character's arms as well based on the arm span. So here I actually have a pretty lenient arm hitbox. It's just a big box. It figures out the arm span, its angle, and then the height is based on the height of the character. We've also got a system in there for, it's a little bit more accurate, where it does a capsule instead. But for players, it usually feels better to be more lenient. And we use the capsule kind of hit detection for like enemies and stuff, especially like large enemies where you might want to be dodging under arms and stuff. All right. So we can have a look at some of our code that we have here. It's really important. Some of this code, I'm not going to be covering like any basics or anything. I'm just going to be covering specifically the systems code. So no explanation of like what a pointer is or anything. And there's a lot of context stripped out from the game. So while you might be able to reference this, it won't be like a direct copy, especially with also like data validation and stuff, because I've also cut out like pointer checks just to make it more concise. This is pretty hard to see, but this is kind of a general diagram of what we have. So this is, we have an anim notifier that determines the damage state for an attack. That throws over to the character, which then activates each weapon, because sometimes you may have an attack that activates multiple weapons. And then the weapon is the biggest thing here, where it updates the collisions, does the collision, caches the animation data. And we have a couple structs. One struct is just the location and the rotation for each for the sockets, as well as the frame time. And we also have the collision data there as well, which also has a relative location, rotation, the shape itself, and also a last location. And then we just have the weapon blueprint and how that connects up to the mesh and stuff as well. All right. So jumping into actually caching the collision data. This happens either on the begin play or changing owners. Here specifically, going over the body setup of a mesh component. It can be static mesh or skeletal mesh. If it's a skeletal mesh, you might end up like looping over multiple bodies. We typically only have our weapons collision on the root body, and any kind of like physics stuff or like a like a dangling rigid body or something is like separate, and usually not taken into account for the collision, the hit detection. We have a relative transform here, which is only relevant for skeletal mesh components. It's just the root body really, because it can be offset from where the actor is. And then we call out to a lambda, which is, jump into here. So when going through collision data on a mesh, it's broken up into multiple different kind of element types. And these elements, they don't really have any correlation to each other. So here's the box element. And even though it's quite similar, the spheres and the capsules have to be handled differently. So I'm just going to cover the box element here, and it's pretty similar for the spheres and capsules. So initially, we just grab the extent and scale it up. This total scale value is the total scale of the mesh, which includes like the character size and everything. And also their relative offset from from the root body there before if it's a skeletal mesh. Oh yeah, and the total scale also includes, if it's like an inflated player collision and static, and that also gets factored in there. Then from that data, we can make a collision shape, which is a lot friendlier to use. And we can absolute each of the values. One issue we ran into, which is just, it's really just like a config issue that we can just fix in code here, where if any of the elements or the components of this shape is negative, we don't get like any trace at all. Like it completely just fails. And we were completely like confused why, but yeah, that's why. So it's really important to make sure your collision shapes are positive values. So we just absolute all the values there. Then we can figure out the center and the rotation. It's important we have to rotate our location based off of the relative offset again. And then we can just add that data into our like local cached collision data container. And we do that for spheres and capsules as well. All right. And this is just the absolute thing. The nice thing about collision shapes, they use a union, so we can just apply an absolute to every value inside the box, and it will also apply to the capsule and the spheres. All right. And this is pretty much the same thing, but what it looks like for like a U-shaped component. Here we actually have the total scale value and how that's figured out. There's probably a better way to determine if it's a player or not, but we only have one player character. And because it's a shape component, we can just directly get that F collision shape and then scale it up and absolute the value and throw it into our cache. All right. So now that we have like the collision data, we can move on to caching the animation data. So this begin damaging event, it comes from that animation like damage state kind of notify, then through the character and whatever, to all the weapons that need to be triggered. So there's also a lot cut out there, but what's relevant here is we first like reset all our data up front, and then we can start caching. So this cache damage state data, this is the function that actually caches the transforms for the socket. And we'll jump into that in a second, but here we just get like the weapon socket, and then for the arms, we get the arm sockets. Here we have some logic that figures out if it's the main hand or if it's mirrored to the left hand. And then after everything's cached, that's when we can turn the tick on and start actually processing. But let's have a look at the damage state caching. So there's a lot of upfront like figuring out data. So there's probably one or two more slides on this. So we start off by grabbing our animation, notify, the character, its mesh, and then we can then figure out, okay, we have our socket, and we want specifically the socket's bone index. And then from the socket bone index, we can figure out the mesh bone index. And then we can also figure out our anim instance and get the current anim montage. We use pretty much explicitly anim montages, and we only let our damage states be placed inside anim montages. And this is because you can have multiple anim sequences in one montage. To keep it simple. All right. There's some even more figuring out data. So from the montage, we can get our anim segment and our anim track, and then we can get our sequence from that. And then from the sequence, we can also figure out which skeleton is also doing this. And then from our skeleton, we can get that mesh bone index from before and get the literal skeleton bone index. And then once we've kind of validated all that data, we can actually start using it. And first we create a start and an end time. So that's the start of our notify, and then we have to offset it by the start of the enum segment. This is because the enum sequence can actually have an offset start time as well. And that doesn't get like automatically figured out there. So we have to do that ourselves. And our end time is just the start time duration. All right. So now we can start initializing our skeleton data as well. So this for loop, it just runs over each of our skeleton's bones and then adds them into another array of a different type, the bone index type, which is like the type that we end up wanting. Because I think there's like a bunch of different bone index types. There's integers and some other kind, but yeah. And from there, we can also create a bone container where we initialize our required bone array, and then also set up some parameters like we want to use raw data or raw animation data or not. Ideally, we just never use raw animation data or the source data, because as soon as you go to cook build, that data isn't available anymore. And we also want to have retargeting enabled as well. More initialization. So here we're initializing like the pose structs. So we pass in our bone arrays and things. And specifically for the enum extract context, we want to be starting, that 0 is like our start time, and the true value is whether or not we're using root motion, or we allow for extracting root motion, which we definitely want to have. We can initialize everything and create our base pose. So here we have if pw enum pose. I don't actually show the code for this, but it is almost directly a copy paste of if enum pose in the engine. The reason why, there's two reasons why I had to kind of do that. The first reason is it's in an editor-only module, so it won't work in the game. And the other reason is because a lot of the things we want are private. So I reused the code and friended my weapon class to minimize the amount of changes I would have had to make to the engine to make this possible. Enum pose is really just like a nice generic like wrapper for enum poses. Blueprint friendly and things like that. And it also doesn't have any editor-only reference code, so that also works. Okay. So now that we have all this data initialized, we can also clear our array so it's nice and empty. And we can start actually sampling the animation data. So in the GIFs and everything, there was like a total sample count of like 30 samples. You may want less, you may want more. You might want to make it configurable. We've just been using 30 for all of our attacks. And from here, we can figure out, okay, we're at sample 0, and we can get our specific time and the animation from that by just looping between it. And the animation system is specifically time-based here. Like you can have animation frames, but you're almost always going to be interacting with the animation system with times instead of frames. It's just part of how the engine works. And especially because of enum montages, because the sample rate for enum montages by default is like 1,000 or something, where the sample rate for enum sequences within the montage are usually like their default frames per second. So we can create and in place our damage state data with the time. So that time is like what time do we have to reach before we can do that sweep. We adjust our context, the enum context from before, to be our current time. And then we create a copy of the base pose that we created before. And this is Yeah, so we have the base pose, and then now we have this new copy of the pose that we will be changing into our target pose in the animation. Oops. And then after that, depending on if the animation is additive or not, we can set our pose. The only difference between additive or not is non-additive is just reset to the ref pose, whereas the additive is like relative. But yeah, that'll get our pose and everything. All the magic's done in the anim pose struct, which is nice. And then after that, we have our animation data all ready to use, and we can grab our relative transform for the specific slot that we want, the specific socket that we want, and add that to our damage state data as well. So the order here is pretty important. We want to be combining our relative locations, like the relative transforms like base location here, which is just the bones location, and then adding that relative socket location. And then only after we've combined those relative locations, we can add the scale as well. Because if you do the scale too early, it'll really screw it up. And same thing with the rotations, although it's kind of backwards with rotations, where normally you add your relative rotations onto the world rotation. Here they're both relative, so it's just combining them, however. And getting added to the world rotation that gets done later on. But that is basically it for caching the data. We now have all our collision data. We have all of our like the socket data for our weapon, for our arms. And now we can actually do our sweeps each frame interval that we had before. So on tick, this function is like a do collision function, where we first set up a bunch of data, and we set up all this data within the do collision, and then we branch out into separate functions for the weapon collision and the arm detection. So just having all this up front makes it a lot more performant. Just all the data is already there. The function can work with that. So we figure out our kind of owner's location, rotation, the current time of the animation that we're at. The location here, it's pretty important that it's the root location rather than the actor location, because the character's actor location is in the middle of the body. But all of our animation data and transforms are relative to the root rather than the actor. And we also have here some look at rotation stuff. Our look at rotation is important for our game because we want to be able to hit things down below or above us. It may not be applicable to you, and a lot of the math actually gets done elsewhere, but rotating the collision detection up and down is important. And we also have a lag behind value. And this is just, is the amount of damage state data that we're going to process this frame greater than 1? Then we'll most likely lag behind. All right. And then we can actually start looping over our weapons damage state data. It's like if we've surpassed a certain amount of time, if we haven't triggered it already, we can just call into the function. And yeah, this is the function. So whenever we process this collision data, it's kind of like, it ends up being kind of a loop, doesn't it? So for each weapon state data now, once we've hit it, we now have to go through each of the collision datas and perform individual sweeps for those. So first we figured out start and our end, which and also the rotation of the sweep as well. So first we figure out the rotation because it's the simplest, I think. And this is where the order of operations really comes in. We start with our owner rotation, which is in the world. And then we combine each of our relative rotations from the collision or the damage state's like rotation. And we also factor in our look at rotation as well. And we also have to correct the collision location as well. So we end up rotating that vector as well by our relative rotation. And once we have the rotation, it's pretty much our final location is pretty much the same between both of these slides, but here we're actually setting the last location, the last known location. This is because we're going to be doing sweeps from the previous location to our current location each time. So if our last location is not valid, then we have to reinitialize that. So here we just figure out the location like normal. It's relative locations, and then they rotate it, and then add it to our world location. And same thing for our end location. Yeah, it's the same order of operations here again. It's just a little shorter. And after we have that, now our start location is the same thing as our end location, as our previous location. And then we can actually just do our sweep. One thing here I'd like to point out is the ECP damaging weapon thing here. That's actually our collision profile. And one thing we like to do is we chuck most of our collision profiles and custom trace types into defines. So it's a lot easier to keep track of them. So instead of having like a string literal where it's like text damaging weapon, we have it all like in one nice and easy to maintain folder, and we can just reference it by name there. It's not shown here also, but I also use trace tags quite often for debugging. So assigning a trace tag to your collision query parameters is really helpful. And then after we've done the sweep, we can add that to our like final results and then set our last location to the end location. So next time we go around, we have an accurate previous location. All right. And now moving on to the actual ARM data. The ARM data is thankfully a lot simpler because the ARM data, we only have like one collision sweep to do. We don't have multiple from the weapon. So we can just immediately figure out our start and our end location using basically the same math where we compound the relative and then add the owner or the world location at the end of that. And once we have those two locations set up, we can figure out our arm length, which is going to be the length of our collision shape. And then we create our collision shape based on the height of the character and the arm length. Now the radius to use is actually, it's kind of an arbitrary number. You can set it per weapon, and it's just, or per character even, where it's just, this is the width of the character's arm. And from there, we actually have our arm check location and rotation. So this is because we have our wrist and our shoulder that's being used as reference, but we can't do a sweep from those locations. We have to figure out the middle point between those two locations and sweep from there. And our rotation is just like the direction of the shoulder to the wrist. So if all that's valid, then we can set our, if we have an invalid last location, we can set that to our current location. For all of this, it's like basically the first frame is just is not like a sweep. It's basically just an overlap at that point because it's just in that one position. And only in the next frame when we move forward, then it would do the sweep from the last location. And yeah, now we can just sweep just like before and add the results and set our last location. I didn't really end up needing this, but I wanted to bring it up anyway. Hash containers are really helpful. My idea initially was I can reference like our collision data by name or something and be quicker there. But hash containers like T-sets are really helpful for minimizing the CPU cost when you're having to look up data inside of like a container. The only thing you need to really implement to make use of them for custom data types is this get type hash function, where you just implement your own override for the function. And here, our whip and collision shaped data is, like, it's really easy to make a hash out of it. We just get the hash of like the if name of the collision. But yeah, we didn't end up needing this, but I think it's really worth mentioning for performance sakes. All right. So after going through all that, with some reflection, there's quite a bit of reflection. I think the system could really benefit from like being async, possibly. We tried async at first in the previous iteration of the system, and it didn't work out so well with like race conditions and things. But I definitely think there's a way to make it work. Like there's a lot of sweeps going on. So being able to parallelize that would be really, really good. We sort of have this already, where this next point, leg redundancy is a fallback instead of all the time, where because this kind of system doesn't work very well with physics-based weapons like flails, because we're only pulling out the animation data, we don't have like any of the physics data to work with there. So the way we have it is we just do completely real-time, like last location, current location, no regard for the cache data for our flails and other physics-based weapons. But if we get lagged behind, then we fall back onto that. And I think just in general, that might be a better solution, just for like all weapons. And even more caching. So there's a lot of data that gets figured out at the beginning of the begin damage event, and at the beginning of our do collision event that we could probably offset into some variables as well. Just minimize as much as possible that we need to go out and find some data in some other object and risk like a cache miss or something like that. And the next point is animation curves. So one of the cool things you can do with animation sequences is like modify the animation within the sequence itself. But the system kind of doesn't have any regard for that. It only references the raw or compressed data. So it has no regard for that. And that has been a little bit unfortunate because our animator really wants that. I haven't been able to figure out if that's even possible, but it's definitely worth looking into, I think. And our debugging could be a lot better. It's a difficult thing to figure out, I think, debugging a system like this. At the moment, all we have is like debug traces and the trace tag, which does those white boxes like in the GIF where it shows you the representation of the sweeps. But that's kind of all we really have. If something is poorly configured and we miss a swing, so it's really, whenever that happens, like someone has to actually go in and spend some time to debug and figure out what's gone wrong there. It could be a config issue, it could be a system issue, it could be a bunch of different things. So I think definitely spending some time to improve that would be really good. All right. And there may actually be some other improvements. Oh, profiling. So there was a pretty minimal amount of profiling done when working on the system. Definitely need to do a lot more profiling to figure out the benefits between each type of system, what is more applicable for your game, and because yeah, like every game is going to be quite different. So while this kind of system works for our game, it might not work for another game where you don't need something as complicated. And so being able to profile and figure out like
is this performance hit even actually worth it? That's definitely something worth taking in. And yeah, there might be some other improvements as well to the system. I think as an industry, we really thrive off of taking inspiration of each other and talking and sharing ideas. So I think, like, even after this presentation, whatever, if people approach me or share this is better, whatever is better, I think that kind of improvement is really, really beneficial. All right. But yeah, so any questions?